Oh, like you can hear me? Oh, yeah. Yeah, I mean, like, wherever I talk, I always try to make sure I'm near the mic. I don't know. There's one there, some here. But... No, that's fine. Should we, like, call this to order? Okay. Okay, guys, we're going to get started. So thanks, everyone, for coming out. Jen and I just wanted to say a few words about ANRW and the process that brought us all here today. Okay, so a note about IPR. The IETF intellectual property rights disclosure rules, the note well, do not apply to this workshop. They do apply during IETF research group meetings. So if you have questions about that, please ask someone from IETF. That's a note about IPR. We're streaming live, so talks will be recorded and posted on the IETF YouTube channel. You can see the URL there on the slide. And obviously a big thank you to our sponsors, Akamai, Comcast, ACM, and IETF. Let's give them a hand. Yeah. So the goals here is to help inform practitioners at the IETF of academic research that might be relevant to them, and also to help folks working on research problems, help them transition to practice. So communicate ideas with practitioners, get a sense of where research fits in terms of standards, and sort of to act as a gateway between, academic research that we're doing at universities and hopefully the standards process going forward. So, the goal here is really to sort of bring research into practice. We've got our organizing committee. So if any of our program committee members or steering committee members are here, if you guys would stand up, can we thank our program committee? Thanks, guys. Well, thanks for all the hard work doing reviews and discussing. And as a result, we now have a nice program. So some statistics. We've got 2 tracks. We've got invited talks, and we also have regular paper submissions. So we had 13 talks that were nominated, and we ended up I believe we invited 4, and 2 have ended up in the program. We had 26 papers submitted to be presented. These were reviewed and then discussed at a program committee meeting, and 13 of them have been accepted into the program today. So that's what you have to look forward to. Oops. Oh, no, it didn't. Okay. Anywho. No, you can just do it.
I'm going to try. Hello, this is not my normal voice, but I hope you can understand me. Just a very little bit about the IETF and the IETF. These are 2 bodies, not one. The IETF is the body that publishes standards and standard tracks RFCs. This is what you typically think of as the body that handles standards, basically. And the IETF is a sister organization that does relevant research for the IETF. Next.
Okay, sorry, I just want to go back a slide for a second. A note for presenters. If you have your slides in PDF, can you please email them to the email address here, irtf-chair@irtf.org. PDF format. These will be posted on the workshop webpage. So this is a good resource for people to look back later. Please get those sent in. So IETF and RTF. Do you want to talk research groups?
So the IETF has several research groups, and while you're here, you should make use of this opportunity to see if you're interested in the activities of any of these research groups. And if you are, reach out to the chairs talk to them, find out if you can contribute or pick up ideas from being part of the research group. And the topics are pretty broad, and there are new research groups that get chartered periodically. So please look into that, and that's the IRTF. Moving on. The IETF has is where you would go to take your research work if you want it to become standardized, if you want it to be adopted by various industry participants and so on. That's where you would go. And here's a brief informal overview which Sharon put together, Sharon Goldberg put together last year, and we're sort of cannibalizing it here. So the idea is that, let's say that I have a draft that proposes how to do, faster than light transport with Quick. I can write it up as a draft. Anybody can write it up as a draft. And we do have such crank drafts as well. So surely yours will do better than that. And you find a working group, you post to the mailing list, you basically get involved, you bring it into a mailing list, and then you eventually get it adopted by the working group. That requires work. Getting there requires a fair amount of work, and that work is just consistent revising, presenting, and again. I won't just walk through this, but I just want to say that there's a process. You can figure out what the process is. Next slide. Oh, sorry, before I get to the talking a little bit more about the process, go to the next slide. Yeah, this is good. You can basically, you develop your research ideas in the IRTF and you bring them to the IETF for standardization. And the most important aspect here is find at least one IETF native co-author. This is a person who can help you navigate the process. You don't have to understand the process I just showed you. They can help you navigate and understand this, because typically the process tends to be very different depending on the working group and the work that you're doing. It can be different. The amount of time it takes can be quite different. Can you go back one? For example, here's TCP Fast Open. This was a draft that was proposed by people at Google, and it took about, how long is it? Starting from beginning to end, about 3.5 years. That's not, I don't know what the averages are, what the median here is. Somebody else might be able to fill you in on that, but that's not atypical. It can be shorter than that. Your draft can be small enough, less controversial, and can take up to 2 years. But again, you have to get these numbers in your head from an academic perspective, thinking about taking up finished research and trying to get it to a standard, and that taking 2 years can seem daunting, but you have to think about the potential for impact that you can have by getting there, which is that the industry adopts your work and your work actually gets deployed. Next slide. So anyway, so you want to find at least one ideal native co-author, or you can have up to 5 authors. So you want to choose wisely, and you have to keep working on the drafts. Sometimes there's not a ton of work, but you just keep working on them. And finally, the IETF basically works on consensus. So getting people to know your work, to understand your work, to support your work is absolutely critical. Importantly, don't wait for others to pick up your work and standardize it. Make it happen yourself. Next. Yeah, I think so. That's
Okay. So with that, I guess we can dive into the first session. If the first session chair and first presenter want to come up.
Okay, hello everybody. It's my pleasure to welcome you to the first session of ANRW this year. This first session is focused on Quic, which is one of the larger undertakings that the IETF has taken on over the last couple of years. Quic is a pretty ambitious protocol that combines security, application, and transport, and is well underway in the Quic working group. And so we're really happy to, oh yeah, let's switch this over. Do you want to put your laptop here? All right, as we get this set up, let me talk a little bit more about Quic. So the Quic working group has been working diligently on developing this new standard and deploying it and testing it. And so we're really happy to have these two talks that explore Quic and its performance in the real world. So first, let me welcome the first speaker here as he gets set up. So let's give a nice round of applause to Conrad Volsing. Technical issues. We just tested this too. Unplug it and plug it back in. Okay, let's see what we can do here. Yeah, let's. I don't know whose laptop is this? He's got a USB stick with the slides. Should we switch and do the second presenter first? Should we do the second presenter first? Okay. In the meantime, let's switch this out, and we'll have the second presenter go first while we get this the slide set up on the secondary device here. Okay, Fabio, are you here? I just saw you. All right. Sorry about that. We're just going to we're going to move forward.
Okay, can I try the cable too? I'm lucky. Oh yeah, it works.
Magic of Windows.
Yeah.
Okay, so we're going to do the second talk first. So this is Fabio Bulgarella. Let's give him a nice round of applause.
Which microphone can I use?
That one right up there.
Hello, everyone. I think it's okay.
Yeah,
Oh,
we'll get to
okay.
stay up there.
Oh, yeah, thank you. Okay. Hello, everyone. I'm Fabio Bulgarella from Telecom Italia, and now I'm introducing a paper about the performance measurement of quick communication, and in particular about the measurement of the connection delay, the round trip time, in this case using a bit more to validate the spin bit measurement. Can we move that slide? Okay, the purpose of the work is that we are proposing an alternative way of improving the spin bit measurement using only 1 bit instead of the 2 bit used by the valid edge counter. In this way, not all the 3 bits reserved for future experiments are used, but we can use another bit just to implement the measurement of the loss rate. Okay, thank you. Okay, as you all know, the latency spin bit is a simple mechanism that causes 1 bit to spin in the quick header, in the short packet header of quick packets, generating one edge, a transition from 0 to 1 or 1 to 0, once per round trip time. So an observer can measure the distance in time between two different edges and generate one round trip time sample per flow per round trip time. The mechanism is really simple. The server reflects, it set the spin bit of the outgoing packet to the same spin bit of the received last packet. Instead, the client inverts. So every time it receives a packet with a spin equal to 0, it sets the outgoing packet to 1 and vice versa. Is there an animation of the process? But I think that all of you know how it works. Okay, we can go ahead. Okay, spin bit has some limitation. Packet loss tend to cause wrong estimates of round trip time due to period with changes, as you can see in the first image. And reordering cause a drastic underestimate of round trip time, since packet reordering cause the generation of fake spin bit transition, and this can lead the observer to measure a round trip time that is really, really small. Moreover, application limited sender can introduce delay in the edge reflection. So if one of the two endpoints is not sending traffic, the round trip time measure can be really high. These issues are addressed by the valid edge counter, that is a 2-bit validation signal used to mark valid edges. We can go ahead. Okay, the valid edge counter is a 2-bit signal that is added to each packet, and its purpose is to explicitly report whether an edge was valid when transmitted. So basically, the mechanism is really simple. A value greater than 0 is assigned exclusively to valid edges. So when valid edges arrives to an endpoint, that endpoint marks the following packet, the following outgoing packet, with a valid edge counter that is the same of the previously received, incremented by 1. So basically, the VEC is increased every time a valid edge reaches one of the two endpoints. Instead, when an endpoint detects a problem, an impairment, such as a reordered or lost edge, the VEC is set back to 1, so the observer can use this information to avoid completing incorrect measurements. You can go ahead. Okay, the delay bit is our proposal. The idea is to have only a single packet that in our case is called the delay sample, with a second market bit that bounces between client and server. So a passive observer placed on whatever direction can compute the difference in time between these two delay samples without considering any other information. So in this scheme, you can see that the first packet of the spin period is set to 0. Then, as you can see, the green packet is the one that carries the delay bit. And as you can see, there's only one packet that carries the delay bit that can be used by an observer to detect the edge of the measurement. We can go ahead. Okay, the mechanism is really simple. The generation starts with the client that set the first packet to 1, so the delay bit of the first packet is set to 1. Both endpoints reflect an incoming delay sample to the first available outgoing packet. But if the reflection is delayed for more than 1 millisecond, this sample is considered lost and the reflection is aborted. The client has to the client side control is a part of the algorithm that is in charge to verify if a spin bit period ends without a delay sample. In this case, in the recovery process start, and the client waits an NT period in which no delay sample is introduced. Then it regenerates the delay sample marking the first packet of the following spin bit period. This empty period is needed to signal to a possible observer that there was an issue and a new delay measurement session is starting, so it can avoid to completing a wrong estimate of the round trip time. You can go ahead. Okay, the key goal in this case is to stabilize the round trip time measurement that are influenced, as we have seen before, by packet loss and reordering. Packet loss is already solved by the delay sample working principle because a single sample is used just to measure round trip time, and when an empty period is detected, the delay sample is considered lost, so no measurement has to be completed. Packet reordering has no effect in round trip time because we do not have the problem that when a packet is lost, the period increases its width. However, the observer must be able to correctly identify the periods and the related delay sample because when an empty period is detected, that one is the signal that the measurement has to be restarted. So spurious spin edges must be detected by the observer. To do so, we can use a waiting interval that is a simple timer introduced into the observer that is implemented adding a time, an interval made of time. That is used just to reject every spin transition after a spin transition is detected. Traffic calls, this problem is solved using that mechanism that introduce an empty period that, not reflect the delay sample when the reflection is delayed at more than 1 milliseconds. Okay, to test the entire algorithm, we implemented a virtual network using Mininet, and the delay bit was implemented in Quick Go. This is the schema of the network, so we have to switch in each side of the observer and the client and the server. We can go ahead. Okay, as you can see, the delay bit works in the same way as the spin bit and the VEC when no loss and no reordering is introduced into the network. This is because in this case, the first packet of the spin period is the one that is marked with the delay bit. So the edge and the delay bit, the spin bit edge and the delay bit are the same packet, and so the measurements are equal. Okay, we can go ahead. Okay, when we introduce random loss, we can see that in the first graphic that the average round trip time is more or less equal between VEC and delay bit. The spin bit tend to increase the round trip time measured because they don't reject those the spin edges that are delayed more than 1 millisecond. And in the second chart, we can see the number of round trip time samples per spin period transmitted. And as we can see, the VEC perform better because when an impairment is detected, it restarts the VEC to 1 in whatever endpoint. Instead, in our case, we need to leave an empty period to notify the observer that there was a problem. So that's the reason, because we have less sample compared to the VEC mechanism. You can go ahead. Okay, introducing reordering, that in this case is emulated by delaying of 1 millisecond a percentage of packet. We can see that in the average round trip time is slightly higher in our solution, and this is because we don't reject those packets that are reordered, those delay samples that are reordered on the network, but we accept them because we are basing our measurement only in one packet. And if we consider the second chart, we can see that in this case, the valid edge counter tend to reject more samples compared to the samples that are rejected by the delay bit. So we can count on a 25% of valid samples in case of reordering compared to the 2 or 3% that can be achieved with the high reordering rate using the valid edge counter. Okay, the conclusion are that VEC produce one more valid periods for edge loss because, as I said before, it's quicker on restart. And the observer implementation is simpler than delay sample because they don't need timer in the observer. Requires 3 bits, so the entire amount made available is used just for the round trip time measurement. And decreases its performance in the presence of packet reordering. On the other side, the delay bit requires only 2 bits, leaving the 3 bits available for packet loss measurements, and produce more valid period in case of packet reordering, but produces less valid period in case of losses. Moreover, observer implementation need a timer, and this timer is the waiting period, the waiting interval to skip false period. But this is also a trade-off for our solution, because the waiting period duration is also the minimum measurable round trip time. So if we set a waiting period of 5 milliseconds, we cannot measure round trip time that are under this value. Thank you. Is there some question?
I know there are a lot of quick people in the room, so I recommend please coming up to the microphones. We have several to ask some questions.
Hi,
Hi.
hello, Giovanni SIDN. This is working? Yes. Nice work. Just to make sure if I understand it right. So can you go back one slide?
Yes.
So the delay bit is the one that actually measures the user experience. Is this right? And
Yes.
You're right. And the other approach, you're trying to compensate for losses. So what are you actually measuring? You're just discarding those packages, but the network is actually having issues, right? So philosophically, what are you trying to accomplish with that?
With that, we are trying to measure round trip time in a way that is more valid if we consider that the spin bit produce a lot of, in case of impairment, a lot of round trip time measurement that are wrong, overestimated, or sometimes underestimated. So with the delay bit, we can try to validate what are the measurements that can be used to have a real indication of the round trip time.
So, all right. So you're saying that the delay bit is wrong if there's packet loss, but is it really wrong, or is it just like it's reporting what it sees on the network? I'm trying to understand this here.
Is it? Sorry, I don't understand.
Let's say you send a packet and it gets lost,
Mm-hmm.
but it actually gets delayed because the network is congested or whatever. And when you get that response, you get a response back, you're going to have the RTT of the specific packet. And then, that would be different from the previous ones you had. So you have like a sort of an outlier there.
Mm-hmm.
So this would be like equivalent to the user experience, right? That's what the user would probably see too.
Yes, the delay bit just gives some information about that spin period, that measurement. So is another point that can be used to measure the round trip time without incurring the limitation of the spin bit period of the spin bit alone.
All right.
So if you consider the measurement is done in a single packet. That single packet, if it is not delayed in the two endpoint, will bounce between client and server without any kind of problem, unless some reordering during the network, during the journey into the network. So the round trip time measured will be the one experienced by the end user. Yeah.
So I think if you're an operator, I'm just brainstorming here. You're going to have a lot of data points with both approaches, which is great. But if you only have delay bit, let's say, and then you're going to see like a delay of a particular destination you're sending data to, let's say they would have a certain distribution, like a median RTT, and out of a sudden you see there's a spike, there's already a problem in there. So what I'm trying to say, maybe the delay bit is simpler, But if you do like a time series analysis on the data, you already would spot problems in the network. So you don't need a lot of data points like Vic maybe. Maybe delay bit will do the trick. Just an idea.
Yeah.
Florin Barbescu, Broadcom. With regard to the waiting timer that you do introduce of 1 millisecond,
Yeah.
what is the reason of picking 1 millisecond, first of all?
Sorry, can
Why
you
did you
repeat?
pick 1 millisecond for this timer? What is the reason of picking 1 millisecond for the timer that you do introduce?
The waiting period is needed just to filter out spurious edges. So if you set it to 1 millisecond, you'll be able to filter out only those spurious edges that were delayed of 1 milliseconds. So it's a trick to filter spurious edges and avoid that the observer detect an empty period and restart the measurement where that empty period is not really present. It's a fake empty period, so there's no reason to restart the measurement.
So again, for me, it's the duration. So 1 millisecond, let's say, versus 32 millisecond. Why one? Why one millisecond? And I'm giving you the reason. For example, if your axis happen to be a cellular axis, in which you may have multiple retransmissions for one data packet, and the typical number may be like 4 retransmissions. Practically, the data that you may send may have a jitter of 32 milliseconds. So in the moment when your waiting time practically is much larger than the waiting time that you pick it here, I don't know actually how do you do it.
Excuse me, I am Mauro Cocigli. I am the other co-author of the paper. I can add some words. There are 2 different timers. One timer is 1 millisecond. That is the timer that measures the error, to avoid an error in the measurement. If there is because the let me say the ping is made using real packets, not artificial packets, it's possible that our delay sample can be replayed because there is no traffic in the other direction. So the measurement can be wrong, not because the delay is big, but because there isn't traffic that can transport this packet. So if we wait for our delay bit, our delay packet is waiting for more than millisecond, we discarded because we introduce an error in the delay measurement greater than 1 millisecond. So this is the reason. If we can accept an error in the measurement bigger than 1 millisecond, we can wait 2 milliseconds, 3 milliseconds before to discard the sample. It's only to avoid to have error in the measurement. 1 millisecond is the maximum rate that we accept as an error. So if it's not possible to replay the packet for more than millisecond, we discard the sample.
Yeah, what I try to say is that on specific accesses, you may have multiple delays which are much larger than the timer that you picked up here, which may be an issue in this case.
No, the round trip time is independent from this timer. This timer is only to avoid the error. So we can measure also big round trip time. Okay, we can.
Okay, well, let's thank the speaker.
Thank you. Thank you.
Okay. Thank you. So, okay, let's try this again. It's also set up here if you don't need. Okay.
Mac OS works. Other speakers with Linux, beware. All right, so finally we'll get back to the first talk of the session. So everyone give a nice round of applause for Conrad Volsing.
So thank you for having me here. I'm a master student from the Aachen University from Germany, and I will present our paper on the performance perspective between Quic and TCP. So to start this talk, I have a very short recap of the two web stacks we currently have in place. And first of all, this is the TCP stack with TLS and HTTP. And this stack currently suffers from inefficiencies, for example, head-of-line blocking, which cannot be solved due to the stacking. And also, deployment is hard in this stack. For example, TCP fast open is challenging to deploy still, and thus the stack is ossified. To overcome these issues, Quic joins this protocol stack and all three protocols in a single protocol on top of UDP. And by doing so, Quic can evolve without ossification over time, and also can solve head-of-line blocking. Moreover, Quic, one key feature is that it promises to have zero RTT connection as establishment. So regarding our measurements, we aren't the first that did performance measurements on TCP and Quic, and there are already a lot of related work already out there. This is just a small collection. And what up until now, related work usually compares websites or also synthetic websites, and there have been measurements for realistic web networks and also emulated networks. Most of the time, related work uses page load time as metrics, but the overall outcome of related work is that currently Quic is the faster protocol. But when you step back for a moment, you can ask yourself, why is this the case? Because basically Quic re-implements all features that are currently already there. So we found two major reasons which might be the case for that. First of all, Quic is already configured for web performance. And for TCP, there are a lot of tuning knobs you can turn to increase the performance of TCP. And we think that related work up to until now does not tune TCP. Moreover, these two web stacks have two different connection establishments. Quic usually requires 1 or 2 round-trip times less during the connection establishment compared to TCP or TLS. So this is maybe where a second gap is introduced in related work. And when you start to reason about user experience, currently it is proven that page load time is not suited for user perception, so other metrics might be better there. So our goal of this paper is to have a reproducible user-centered performance measurement between these two web stacks, TCP and Quic, and to do that on an I-to-I level. So in the next step, I'll explain how we achieve this I-to-I level. These are some properties these two stacks have usually right out of the box, and you can see Quic TCP is still lacks some configuration. So the goal is to tune TCP to reduce this initial gap. We do so by increasing the initial window and enable pacing for TCP, and we can also use the TCP fast open option for zero round-trip time connections, and also measure with TLS 1.3 with early data. But we won't do so for our measurement because of the following reasons. First of all, at the time of our measurements, TCP TLS 1.3 with early data was not implemented in the Chrome browser, which we use for measurements. And second, TCP fast open is not that deployed. For example, at our university, the firewall still blocks TCP fast open. On the other hand, we don't use Quic with zero RTT2 because we see issues with zero RTT in the deployments too, because there are issues, for example, with replaying, and since HTTP is not stateless as it is promised currently, we don't see zero RTT for Quic coming soon. So still there's one round-trip time difference, but we will discuss this one later in the evaluation. So finally, we use only HTTP2 in our testbed for TCP. And then for the evaluation, I derive these 5 different protocols. We have stock TCP, which is, as reference, the untuned TCP. Then we have a tuned TCP with the tuning from above. And then, since we expect the congestion control to have huge impact, we also have one scenario with TCP and BBR as congestion control. Then on the Quic side, we have a recent Quic version, Google Quic, and also one with BBR. So regarding our testbed, how did we implement this? We used the My framework and modified it to support Google Quic and also the Nginx server. And this Mari framework is already capable of replaying websites realistically. And it also comes with a network layer to emulate different network settings. On the bottom, we have the Chrome browser, which measures our web performance, and this one gets measured by browser time. So before we start our measurements, we did a short benchmark of the performance of our two servers that we have, and therefore we downloaded files with different file sizes without any bandwidth restrictions. And for sizes below 1 megabyte, we can see that both implementations, Google and Anrw-Quic, are similar. And just at file sizes at 10 megabytes, there is a gap emerging. And here we can see that Google's Quick implementation is not that fast compared to Nginx. But for our measurements, this does not impact because our website file resources are usually smaller. Our largest resource is 4 megabytes. So we won't see these gaps in our evaluation and measurements. Regarding network configurations, we have 5 network configurations and one more than we presented in the paper. The 3G network is not in the paper. And we have a speedy DSL, LTE-like connection, the 3G, and then 2 special networks, the direct air-to-ground communication, which is, and the mobile satellite service. And these 2 are measured from other researchers doing actual flights, airplane flights and the internet reception up there. Direct air-to-ground communication uses cell phone, LTE-like network, but with antennas pointing toward the airplane, and mobile satellite service is using satellites. So what do we measure on? We have a set of 38 websites, which is a subset of the Alexa and Mods lists. And as you can see, these websites are quite diverged regarding the size and also the number of IP addresses. And we have 4 different visual metrics which we evaluate on, and these are all measured above the fold, and only page load time is not above the fold. So we have first visual change speed index as a metric matching the user perception more closely. We have the point in time when the website reaches the visual completeness of 85%. And also last visual change. So to calculate the difference between our 2 protocols or protocol combinations, we define the performance gain. And this one is, for example, most of the time, the difference between some protocol and untuned stock TCP. And we repeated our measurements 31 times and then take the average and denoted by here the overline. And the performance gain is basically the normalized difference between 2 protocols. So as an example, if the page load time for Quick is 0.5 seconds and the page load time for TCP is 0.75 seconds, then the performance gain would be negative 0.33. So I'll go now through our networks and our results. First of all, in this plot, you can see all 5 metrics side by side. And on the x-axis, we have the performance gain compared to stock untuned TCP at 0. Note that negative performance gains show the speed increase. On the y-axis, we have CDF over all 38 websites. And what you can see here is that tuning indeed already increases the performance. So we can show that tuning should be done for comparing websites. But still, Quick outperforms even our tuned variant. And what you can see also here is that the congestion control does not have a huge impact because the lines for BBR are mostly overlapping with the Quick lines. Still, we derive from the steep curves that the website structure in general has here a low impact on the overall achievable performance. So next is the LTE network. This one is a little bit slower, but not that much slower in bandwidth. And here we see similar results to DSL, and only the gaps in performance gain are increased. So there is no much to see here. But when we look at the 3G network, where the bandwidth is decreased even more, we have higher round-trip time and a small amount of loss, then we can see that the tuning impact of TCP is decreased, especially when you look at last visual change and page load time. But still, Quick is better here. And we can see that the variability rises. Here are the curves aren't that deep anymore. and maybe there are some other aspects too. So when we decrease the bandwidth even more, this is the network with the least bandwidth, we can see that first of all, tuning becomes a toss coin here, and tuning does not really impact anymore. And we think that this is the case because the initial window increase might lead to early loss here in this network. Still, Quick performs very good here. We have high round-trip time and a lot of loss already, 3.3%. And we think that Quick performs that good compared to TCP because Quick does not have any head-of-line blocking, and it has larger seg ranges, and thus it can also detect loss. So the last network here, we have an increased bandwidth again, and here we can see that tuning is again profitable, but here the round-trip time and loss has increased even more, so we have 6% loss in our packets, and we can see that here for the first of the time BBR outperforms Cubic. So when you track the green line for TCP BBR towards the end, you can see that at patch load time Quick BBR and TCP BBR are quite similar, so the congestion control here impacts more than, for example, the protocol choice. Still, Quick with Cubic is very fast, and we think that this is the case again because of no head-of-line blocking, larger seg ranges, and so on. Okay, to conclude these findings, here we have on the y-axis the mean performance gain over all websites, and on the x-axis all protocol combinations, and then the colors denote the different networks. So for the first tuning TCP versus untuned TCP, we can see that except for one network, tuning TCP is profitable. When we compare untuned TCP against Quick, then we see that this is the largest performance increase, and when you take into account tuned TCP and Quick, then the performance, of course, is limited. And when we look at TCP tuned and BBR and Quick, and with Quick BBR, then we can see that there's usually no performance gain except for our network with the high loss where the congestion control impacts most. And for the other networks, we see that Quick is still better, but sometimes, again, congestion control is for the MSS network more important. So up until now, we have only looked at network characteristics and averages over websites. And we know how large our websites are, how many IP addresses they have, and, for example, how many resources need to be downloaded. And thus, we can also reason about what might impact performance too. For this talk, we picked the influence of the number of resources, because we think that this one might impact most because of the head-of-line blocking, which is related to resources. And here on this plot, you can see on the y-axis all of our websites that we have in our set. And on the bottom, there are the websites with the least amount of resources. And on the top, for example, the morgen.be website has the most amount of resources. And on the x-axis, you can see the difference between the Quick and TCP protocol or with BBR. And this time not for performance gain, but in seconds, just to make the difference more clear. And as we can see here for first riddle change, the blue line, this one is closest to the 0 line difference. So for the first riddle change, the impact of the resources does not have such a huge impact because already at first riddle change, there aren't that many resources loaded. For speed index and riddle completeness, we see that for websites with few resources, there is no real impact, but there are some websites with high amount of resources where riddle completeness and speed index is impacted most, and there are also some outliers. One outlier is very exceptional because here the New York Web Times website, here we have a large shift for riddle completeness towards TCP, where TCP is better. And when we take a closer look at this website, we find the reason in how the website loads. So here you can see that the New York Web Times website has an ad banner on top, and we were able to reproduce the time when this banner loads, but not the actual content of the banner because we couldn't reproduce the ad network. So let's have a short look at this video. So what you can see here is that basically both websites load similar, but TCP manages to load the upper banner first. So this triggers then the visual completeness event, and Quic takes some time to load the upper banner. And so maybe visual completeness isn't the best metric because it depends, for example, on the banner shift. And all other elements in Quic might still be present, and just it is the banner popping down late. So what is still left for the evaluation is that we have a difference of round trip time in our measurements. So maybe this would explain the remaining gap between TCP and Quic. And our idea was maybe we can subtract out one round trip time from the page load time, since we know how we configured our round networks, so we know the round trip time. But as it turns out, this is not that straightforward because a lot of resources and websites have to be downloaded via a lot of different connections, and so we cannot simply subtract out one round trip time. Luckily, in our set of domains, there are two websites, Wikipedia and GNU.org, that rely on resources of only one single IP address. So here we can subtract out one round trip time for the connection establishment, and then we have reduced this gap. When we do so, we get these results. Here you can see for the different networks and the websites, the difference in page load time. And again, negative values are the performance increase for Quic. And as you can see here, that for the fast DSL, LTE, and 3G networks, usually the corrected difference is very small, within milliseconds. And in terms of round trip times, the difference is below one round trip time. So Quic and TCP are similar fast. There is one exceptional case here for the Wikipedia website where the difference is still a lot of round trip time, 3.8 round trip times. And here we can argue that maybe this is the case because of head of line blocking or so. For these networks, there are also two cases where TCP is now faster slightly. For the MSNS network, we had to look a little bit more closely because here the congestion control again impacts most. And on the top table, you see Quic. And when we correct the round trip time difference here, still Quic is faster. But on the bottom table here for BBR, we can see that there's also now a case where TCP is faster for Wikipedia, and still the round trip time difference is below one round trip time. So to summarize, we found that tuning TCP is not negligible when we compare two different web stacks. Still, Quic outperforms TCP, but the gap gets narrower. And we can argue that the remaining gap can be explained by the difference in the connection establishment between TCP and Quic. Moreover, there are some cases where the congestion control matters much more than protocol choice sometimes. Okay, some discussion. We think that Quic is not primarily built to improve the performance, but to perform well, as we saw. It performs quite well. We think that Quic's main reason is there to enable evolvability of the web stacks that are currently there, and especially on transport layer. And one open question, which also arises from the video, is we can measure these differences, but how do users perceive these differences? Because maybe these differences are too small to be even perceivable for end users. So much about that. Thank you for your attention, and I'm happy to answer your questions.
Hi, Anand here from Verizon. Talking about user perceived impacts, have you or are you planning to look at video and then look at rebuffer ratios rather than just page load times?
We are currently working on a study how users perceive Quic, and the results haven't been published yet. So we are working on the field of user perceived quality of experience of Quic.
Thank you.
Hi, Chris Box from BT. I do design for the EE mobile network. This is really interesting data. I'd just like to ask how you're simulating an LTE network. So are you assuming a constant bandwidth?
Can you speak a little bit louder? What's your?
I don't know if this is
The question was,
How are you simulating LTE?
we do not simulate LTE. These are just the properties. So we don't have the complete LTE backbone. We only set the bandwidth, delay, loss, and queuing sizes in our network emulator.
Right. Okay.
So we don't emulate the complete LTE network here.
Right. Okay. So in reality, LTE, even with a single carrier, can change its bandwidth from millisecond to millisecond, and with multiple carriers aggregated, it can change in much larger chunks. So possibly a topic for further research would be how does the congestion control algorithm influence that, and what's the performance difference there versus what you simulated here?
Sadly, we didn't look into changing network conditions, so we also didn't go deeper into the results of the congestion control here. So no, we don't know how changing the bandwidth over time impacts the performance.
I think it can have an effect. I'll try
Yes.
and talk to you afterwards.
Of course.
Thank you.
This is Yoshi Nishida.
Can you speak a little closer to the mic, please?
Okay, sorry. This is Yoshi Nishida. So, in my understanding, the main reason that Quick outperform TCP is the connection established speed and the headline blocking issue. Am I correct?
Yes, these are some major improvements that we see for Quick, and also, for example, the larger SAC ranges that are there in Quick, and also for BBR and so on. BBR can oversee loss, static loss, and also Quick is able to Quick can see whether it is a retransmission or not, which can also help. But we weren't able to confirm these findings because we have no tooling to look inside the encrypted packages.
So have you tried bulk data transfer measurement? I mean, just sending a large file and then comparing Quick and TCP, fine-tuned TCP and Quick. And then do you see some difference, or the result is also almost the same?
So you think mean that we just benchmark one single file?
Right, right, big file.
No, we didn't do that because we concentrated on web performance here, what you will get in your web browser. Okay. So we had our speed performance measurement for these two implementations in the beginning, but this one was without any network impacts.
Okay.
Certainly not.
Okay, one last question, sorry. Just out of curiosity, I think, IETF Quick will use Neurino as a congestion control. Why you are using Quick? Cubic, sorry.
We choose Cubic because it was implemented for the Google Quick. So Google Quick comes with Cubic and BBR currently.
Okay.
Yeah, Florian Babescu, Broadcom. A few questions. One, do you happen to have values for the maximum size of the reordering buffer in both cases?
In our network emulation, we don't have reordering. We only have buffer sizes, and we had buffer sizes of, okay, I can tell you, 12 milliseconds for DSL, and all the other networks had a buffer size of 200 milliseconds.
So we don't estimate it in bytes?
Yes, we recalculated that for the round-trip times.
Okay, so it's in the paper, I assume?
Again, so
it is in the paper specified, I assume?
Yes, in the paper is also in the table there was maybe some slides back. Here is the queue size, which we defined in milliseconds.
And similar like the previous speaker regarding the LT, I believe that if you want to continue to do some of these evaluations, it would be interesting reporting, for example, in the context of Z-axis, like varying different type of number of retransmission over Z-axis with different error conditions model. And I would actually like to see how Quick may be able to solve it.
So for forward error correction or something like that?
Yes, so LT model, it's way too generic what you say there. Yes. I don't understand anything.
Yes, it isn't a real LTE network. It just has the properties of it. So,
what are properties of LTE?
Yes.
Hi, Lars, nice work. I've one question that's sort of to you, but also to the G-Quic people. So as far as I know, at least at some point, the cubic implementation in G-Quic was actually tuned to be as aggressive as 2 new Reno flows for TCP because of some YouTube thing. And so I wonder if this explains some of the benefits you see. Have you looked into this? I mean, you could also sort of, you tuned the kernel TCP to be as aggressive as 2 Reno flows, right? You could see whether that made TCP perform a bit better when it competes with G-Quic and cubic. And I don't know what the BBR is optimized for. It might similarly be optimized to be as aggressive as 2 flows.
Yeah, maybe one note. We don't have competing flows here in our measurements. We only have competing flows against the different IP addresses and resources.
Sure, but you still open the window faster.
Yes. Okay.
Yeah. In terms of, yes, I think probably the default is still probably to do the 2 connection emulation, but BBR mitigates that, and the BBR implementation in TCP and Quic should be as similar as is reasonably possible. So there's no like extra 2 connection graph.
Okay.
That was one of the explicit goals of moving to BBRs to get rid of that.
Thank you.
Okay. It's great to have the people implementing it in the audience. Okay. All right. So let's thank the speaker. And this is the end of the first session. So there's going to be a short break. And but please be back in your seats, ready to listen in 10 minutes.
Excuse me quickly before everyone leaves, if the speakers for the next session could please come up so we can test the slides and make sure everything's working before we get started, that would be very helpful. Thank you.
Joe? Oh, these are
There is an HDMI here. He's using it right now. Are you doing Dragon Blood?
No. I'm not doing. Just wanted to do a false test.
Okay.
It looks like okay. Hope it will be. Have it on pen drive and send it to YouTube.
Okay, yeah.
It's usually designed.
I got the new MacBook Air a couple years ago, and it had like weird firmware bugs with the HDMI driver. So like I was very MacBook Air, and I got this new one, and it's crazy.
Do you know who did the first one? I know EO, but I haven't seen it.
I figured it may be worth putting you in
Dragon Blood Talk, do you know who's actually doing that?
Did anyone